So one of the areas that has seen substantial work in the last 10 or 15 years is empirical analysis of macro models where you're using a large number of predictors. There's a lot of different ways to think about this issue. Certainly when I was preparing for these talks, forcing yourself to go through all of this literature, I guess, gets you to make some connections that you certainly hadn't been consciously made, maybe subliminally, I don't know. But it seems as though one important theme running through many of the issues that we've talked about with GMM and DSGEs and hack estimation is limitations in the data that we actually work with. The questions that we want to answer are ones that are perhaps a little bit ambitious compared to what the data are able to support. There's basically two answers to that. One is, given the data and the questions, try to come up with better software, that is better econometric algorithms, better distributions that can help you answer it. And the other approach is to see if you can get more data. So in the more data category, in SVARs, that was what I was referring to the other day as thinking about natural experiments or bringing in something from the outside to help with identification. And this clearly falls in the more data or more information category. And for a number of the problems that we face we, meaning the profession, face in a very practical way, such as forecasting, the tools, certainly the time series tools that were available, say, 15 or certainly 20 years ago, were ones that focused tremendously on very small models. And those models proved to be reasonably successful, but they still had some trouble against judgmental forecasts and green book forecasts and things along those lines. And I think one of the big challenges is there a way to take into account all of that information that is used in the heads of experts in a systematic way? And so then the big challenge is, look, in real time or in every month there's 1,000, 2,000 data series that are released, and we look at 6, and those 6 are kind of interesting, but that leaves 1,994 left. And is there anything you can do about it? Well, so as it says here, the idea that you would want to look at all of those series is, in some historical sense in econometrics, somewhere between radical and stupid. And the reason for that is anyone who's brought up on standard time series analysis learns the principle of parsimony, which is essentially work with small models and few parameters and keep it simple. So as Arnold Zellner would say, keep it simple, stupid. His principle is KISS. So, and the thing is quite obvious. Even if you're running a VAR with just a few lags and 6 variables, you start to really have a parameter proliferation problem. So the question then is, how do you go ahead and try to tackle the large amount of data that's out there and make progress? I'm going to talk about 4 areas that have seen work in this. The one that's seen the most work is in the area of economic monitoring and forecasting, and so I'll talk about that in the most detail. But then at the end, I'm going to talk about extensions of that using large data sets for structural vector autoregressions. The buzzword there is FAVAR. And then IV estimation and DSGE estimation using large data sets. Okay, so just to look ahead a little bit, it turns out that a very useful tool for a lot of this is dynamic factor models. Dynamic factor models were proposed by John Gaverke in his dissertation, and in their extension of factor models that were, say, prevalent at the time as psychometrics. Sargent and Sims have an early paper using this as well. I should emphasize that although a lot of what I'm going to talk about is dynamic factor models, there's no particular a priori reason that dynamic factor models would have to be the best way to handle a lot of these questions. And indeed, in 10 years, we might decide or we might have decided that they're not the best way to handle these questions. It just turns out that when you look at a lot of different procedures, dynamic factor models happen to be a very robust, tractable, and in senses I'll make precise in a bit, reliable set of a family of tools that work well in this problem and seem to work at least as well and in many cases better than some of the other tools you might think of using. So that's what there's going to be a lot of focus on that, but I want to emphasize that the focus on DFMs is not in any sense dogmatic or religious. It's more empirical, based on, this was one of several ideas that you could pursue, and it turns out to be one that works pretty well. Okay. I should say also that there's a broader trend, which I hinted at yesterday, and it will come up again in many of the sciences, in the life sciences, but in some of the other observational physical sciences like astrophysics, towards moving to massively larger data sets. So apparently my understanding is that the newest chips for the newest sequencing chips have an individual site on this chip is called a probe. So you smear a bunch of DNA on it, and then it goes to these different probes. And these new chips have 30 million sites. So one observation on a sample of DNA, so if I take some DNA and I smear it on this, or I don't know, they do something like that, it comes back with a vector that's 30 million observations long. Okay, so then you do it for a bunch of different samples, and the data set gets pretty big pretty quickly. We are not at 30 million observations, so the order of magnitudes here compared to astrophysics, where there's quite a few stars that they're studying, and genomics is really not anywhere of the same order. But it is the case that there's some pretty interesting tools that have been developed for these extremely large problems that are potentially of some interest. At least at a theoretical level, they're of some interest, and I'll talk about them. I think as it turns out, we're going to come back saying that the tools developed for genomics don't work as well as dynamic factor models, and maybe there's some reason to think about that, but we'll be able to make that precise. Okay. So why do you want hundreds of series? And so let me talk about this dimensionality from curse to blessing, because certainly for those of you who went to graduate school a while ago, and if you did take a time series course, boy, those were small models and principles of parsimony, and you really don't want to have large regressions. So let me give you an example. This is going to be in some sense, a toy example, but it's going to be a pretty good analogy for a lot of stuff that we'll be doing. So a toy example is where you would have a regression of y on p. Okay, why am I using p? P for predictors and also for principal components, and you'll see why that is. But the key thing is that I want these to be orthonormal, because that's going to make my calculations easy, just for this example, okay? So we're going to have an orthonormal set of regressors, so we don't have to worry about any covariances, and an error term. And these are going to be strictly exogenous regressors, and the errors are going to be IID normal, and that's going to make my calculations for this example simple. All right, so this is not a time series problem, even though I've got some sub-t's, but it's going to be simple. It might be that if you have normal noise, that what this is a model of is these might be wavelet bases or something. These might be wavelets bases that you're trying to do some analysis of signals on. So this would be a model that comes up in signal extraction. Okay. Okay. So if you have, we're going to have a quadratic loss function, simple as could be. And what we want to do is we want to make a forecast. We want to make a forecast using data through cap t of the value of y tomorrow. So it's a single series, and we're going to think about this as being a large number of predictors, and you've got normal errors, and you have squared error loss. All right, so it's a standard problem with the exception that we're thinking of p as being large. Now, one thing you learned in graduate school is that if you've got a ton of regressors, don't just throw them in OLS, because that's a bad idea. Okay? It is a bad idea. Okay, so we're going to go through why it's a bad idea. You probably didn't think you needed algebra to know that's a bad idea, but we will do it anyway. All right? One way to make precise that it's a bad idea is to say that in a particular, so here's the loss you make. If this is your forecast one realization of your forecast, and this is the true value. That's the forecast error, the mistake you made. You square it, and that's how bad you feel. Okay? This is how bad you can expect to feel on average when you make forecasts using this procedure. Right? That's what is called the forecast risk, the so-called frequentist forecast risk. So it's how bad you expect to feel on average. All right? Now, I'm going to do a little bit of calculations. How bad you feel on average, well, there's two reasons you can feel bad. One is because the future just, stuff happens, and you didn't know about it, and it's just in the future. Well, there's not much you can do about that. And the other reason you can feel bad is because you used a lousy forecast, and you used a lousy estimator of the coefficients. All right, so if you use a lousy estimator of the coefficients, well, that's going to make you feel bad because you're going to have a quadratic loss that's associated with your forecast based on this bad set of the coefficients. Well, you can break these out because what happens tomorrow is unrelated to the data, what you used in the past to fit, to estimate the coefficients, the IID data, right? So what happens tomorrow is unrelated to the past, so these are two separate things. You can break them out. And you have two parts to your forecast risk. You have a part that you can do nothing about. That's just the way it is. And you have a part that you can do something about, which is the risk associated with this particular estimator. The risk associated with this particular estimator is the inner product of it, expectation of its inner product of this vector, or sometimes referred to as the trace MSE risk because it's the expected value of the trace of this. It's basically the MSE matrix. It's the trace of the MSE matrix, so it's the difference between your estimator and the true value. This isn't a variance, right? It's not the distance between the estimator and its expected value of that estimator. It's the difference between the true value and the estimator itself. So this is an MSE. It has variance and bias built in. Yesterday, I suggested that this risk function is a risk function that is not an appropriate one for point estimation in DSGE models, that we're actually not interested in some bias-variance trade-off in DSGE models. We want to know what, the Calvo parameter is. We want to know it. Here, we actually couldn't care less about the coefficient on the ith predictor. We're not interested in that at all. We are interested in one thing, which is not feeling bad about our forecast, at least on average. All right, so that says that that this is a pretty reasonable loss function for us to think about. Since we can't do anything about tomorrow, at least we can do something about the procedures we're going to use to estimate delta. Okay. All right, so that's our forecast. And I should mention that if you're following along on the slides, you've probably already noticed about 20 discrepancies between what's on the screen and what's on your slides because of a large number of typos. But since nobody seems to have been paying attention to the handwritten stuff or the stuff on paper, that's perfectly fine. The revised version will be on the web in due course. Okay. So let's just to make this thing concrete, sort of obviously, if you knew the true value of delta somehow, then of course you would use it, and this whole term would be zero. Your frequentist risk, your forecast risk would be, your estimation risk would be zero because you haven't made any mistakes. So in that case, you would get what we can call a first-order efficient forecast, and it would be as good as if you knew the true ones, and you actually would know the true ones. If the coefficients were consistent, then again the estimation risk goes to zero, so you would have a forecast risk that doesn't go to zero, it goes to sigma squared epsilon, and the forecast would be first order efficient. But of course, now that's actually a reasonable thing to think about if you only have a handful of coefficients. So if the sample size is large and you only have a handful of coefficients, thinking about these coefficients being consistent for the true value is probably not unreasonable. But the situation we're going to be interested in is trying to exploit a large data set where there's a lot of information potentially. And in that case, OLS is not going to be first order efficient. And in fact, because by the exogeneity of the regressors and the fact that I assume normality, we have an exact distribution for what delta tilde, our estimator, is. The OLS estimator is exactly this distribution. It's the textbook x prime x inverse sigma squared distribution. There's not supposed to be a t here. It's p prime p, and there's not supposed to be a t here, and that's going to result, since this is orthonormal, that's going to result in a t there. So this equation is correct. All All right. Okay, so that looks pretty good. I mean, it looks like you would have a variance getting smaller, but the trouble is there's a lot of these things. So if I compute the trace MSE, it's centered around the right thing. So in this case, there's no bias. And then I just compute the trace MSE. Well, that's going to be the trace of this matrix here because there's no bias term. Well, the trace of this matrix here is going to be sigma squared epsilon over t. That pulls out. But then it's the trace of this n by n identity matrix, so I have to add up n terms, and I get n over t times sigma squared epsilon. So if I put that together, the forecast risk is n over t times sigma squared epsilon plus sigma squared epsilon, which gives me 1 plus this ratio, n over t times sigma squared epsilon. Okay, so that's actually an instructive formula. What it says is that if you use a lot of variables, predictors, then in fact you're going to get a forecast that can be potentially quite a bit worse than this first-order efficient forecast. All right. So, so a couple of other comments. As I mentioned again, I think the other day in passing, there's a couple of other reasons why you might want to think about OLS as not being particularly good, and one of them is this really amazing result by Stein in 1955, which said that OLS isn't admissible under this trace MSE risk, which is to say that this risk function, okay, this risk function here, if you look at this trace MSE risk function, it turns out that there exist other estimators that have a risk function that is uniformly no higher than, so it's below in some points and it's perhaps the same in other points as OLS. And in fact then, Stein proved that existed in 1955. No, he proved that there must be such in 1955, and then he actually constructed one in 1960, and that's this James Stein estimator, which is a shrinkage estimator, and it shrinks towards 0. So in the area of 0, since delta is being shrunk to 0, the James Stein estimator does better than OLS. And the interesting part of the calculation is that everywhere else it still does a little bit better, or at least does no worse. So the James Stein estimator has a risk function that strictly lies below the OLS risk function. So even if you only have three observations, three regressors, OLS is probably not a great idea. And we're going to be talking about having 100 series, and so this is another reason to think that you can't, not only is OLS not a good estimator, but there exist estimators that are going to be better. Okay, so so if you will, that's the curse of dimensionality part. Okay, so why am I doing this, right? You guys are probably all expecting me to write down a dynamic factor model and to start talking about estimation of dynamic factor models and, how to use binding to estimate the number of factors and all of that stuff. And here I am rambling along about this risk business. And the reason is twofold. One is, you might not know this. It's supposed to be a class. The other reason is I want to impress upon you that there's actually some theory behind all of this stuff, and it's not just people running stupid regressions and seeing what happens when they do simulated out-of-sample forecast exercises, okay? So this literature can get a bad rap if you don't know that there's actually something going on behind it. All right, so here's part of what's going on behind it. Blessing of dimensionality. So I just gave the curse of dimensionality problem, but the curse of dimensionality wasn't a curse of dimensionality. It was just said we didn't use the right tools. All right. So let's use the right tools. And so here's a way to think about what the right tools are. So I'm going to adopt a local nesting in which the parameters are local to 0, and the only reason I'm doing that in this setup is to prevent the R-squared going to 1. If you have a large number of predictors and each one of them is important, you're going to get the total sum of squares being totally just equal to the explained sum of squares. R-squared is going to go to 1 in any of the asymptotics. So this is just a device to keep the asymptotics from being unreasonable. And so these D's now, or equivalent to the deltas, these D's are what we don't know. If we knew them, we'd be in business. These are the coefficients scaled. But what I am going to assume, this isn't an assumption, this is just a definition just take those D's. So take these D's, which are these true population coefficients that we don't know, divided by times square root of t, and just order them from smallest to largest, and then compute an empirical CDF. All right, so you guys know how to compute empirical CDFs. Mark, this wasn't this an empirical CDF? Where you had empirical CDFs that he was inverting, okay? So that's an empirical CDF, except it would be kind of squiggly because it's a step function. All right, so you construct the empirical CDF of those things, and you call it G sub n. And that's just going to be a name. All right, and now I'm actually going to talk about estimators that have a particular characteristic, which is that they're invariant to the order in which you put the regressors. So when you are running Stata or RATs and you have to type in a list of regressors, you get the same R squared whether you type consumption first and income second, or whether you type income first and consumption second as the regressors. I see puzzles. You probably are wondering, does there exist any estimators that don't have that property? And there are. You could write an estimator down that doesn't have that property, but I'm not going to consider them. Okay, that doesn't seem unreasonable to this audience. Okay. All right. So now I'm going to do a heuristic calculation. This heuristic calculation is formally justified in some references that I'll give. Here's the frequentist risk. Okay, the frequentist risk is the trace MSE loss, and so I've now written it out with a summation sign. Okay, and now I've done nothing of interest here except I've divided. I'm dividing by n because there's an n here, and then remember these deltas. I wrote these deltas are equal to di over the square root of t. So I'm just doing local nesting. So delta I is equal to di over the square root of t. I'm doing a local nesting here. So I can change the deltas to the d's, and I can pull out a t. All right. So I haven't done anything. I've just done the substitution. And now here I actually, it looks like I've done something, but I haven't done anything. This is a summation over the d's. The summation over the d's identically can be written as an integral with respect to this step function CDF. So this is again an identity. Okay, so this is writing this in. Okay, but now this is amazing. Let's just look at this for a second. It's an integral of the expected loss with respect to this empirical CDF. We defined this yesterday to be the Bayes risk. Okay, the Bayes risk is the expected value over some CDF, over some prior, of a frequentist loss. This is a Bayes risk. It's a Bayes risk. It's a very funny Bayes risk because it's a Bayes risk with respect to not a prior, but this empirical CDF of the D's. But that's what it is. This is the Bayes risk. This is just that's just a definition. We have defined the Bayes risk to be an integral with respect to some density, or some in this D CDF. Okay. This actually, so I can say that this is a deep link, and I can get away with saying that because it certainly isn't something that we thought of. This is an old deep link due to Herbert Robbins between Bayes and frequentist inference. So let's think about this. I want to find the estimator that's going to be the best possible, and I'm a frequentist, so all I care about is I want to minimize my frequentist risk. I've learned that OLS is a bad idea because there exist things like James Stein when I've got more than 3 regressors that are going to be better. And I don't have 3, I have 100, so there's things that are going to be tons better than OLS. So I'd like to find that function of the data, delta tilde, that gives me the lowest frequentist risk. This is just a series of equalities. And what it says is that my problem, my frequentist problem, is actually the same as this Bayesian's problem. Now, this is a very strange Bayesian. This is a Bayesian like none we've ever met before because your prior is actually the empirical CDF of the true D's. But suppose you were that Bayesian, and suppose this were your prior. if you could solve your problem for the optimal Bayes estimator, it would actually be my optimal estimator. These are the same problems. That's the idea. So this, we've solved the frequentist optimal estimation problem and therefore the optimal forecasting problem under trace MSE loss. And the way to do it is to use the Bayes estimator with respect to the CDF of these parameters. Now, there's a lot of special things about this, like it turns out that the orthonormal regressors is really important to this argument. But I think this is all, but it's all correct under what I've said here. This is, so then you could say, what do you mean? So now we're going to, okay, this is the underlying idea of empirical Bayes. And so what empirical Bayes says is, all right, I want to solve a Bayes problem, but it's a very strange Bayes problem. It's a Bayes problem where I'm actually going to be solving it with respect to some empirical CDF of the underlying true parameters. And if you can solve that problem, then that's going to be the optimal thing to do from this forecasting perspective. Okay, so one way to think about this is that we're going to have a whole bunch of Bayesians come into the room, and all of these Bayesians, because they're subjectivist Bayesians, they all have their different opinions, and they're all going to produce an estimator, and we're going to choose the Bayesian with the best prior. That's a stupid thing to think about. How can you choose the Bayesian with the best prior? And that's not a sensible thing to say if you're a subjectivist Bayesian. But it's actually incredibly sensible if you were at the Fed and you have a committee meeting and people come in with their models and their different priors and they keep coming in and again. And this guy, is always too pessimistic. Eventually, you'd say that's a bad prior. Your prior doesn't forecast very well. This person's always too optimistic. Their prior is just not very good. They're always too optimistic. They don't forecast very well. One of these people in this meeting, one of the people in this room, will produce the best forecast over time. It's logical to think of that person as having the best prior. So that's what empirical Bayes does, is it finds the prior that is going to produce the best forecast, that is to minimize the trace MSE loss. That's not how it does it, but that's the idea. So it's quite well posed to say that one person's prior is better than another's. It's not well posed from the perspective of a personal subjective Bayesian decision theory, but from the perspective of making a forecast, it is. There's an empirical reality, which is the future, and you're trying to forecast it. Okay. So there's a bunch of really cool stuff about empirical Bayes estimators. There's certain senses in which they're asymptotically optimal. That was shown by Robbins. It turns out, so Efron and Morris in a really important paper in JASA showed that the James Stein estimator is actually empirical Bayes. So this thing that I called this James Stein shrinkage estimator can be justified as empirical Bayes. So it's going to give you an algorithm for constructing good estimators. There's a couple of papers in the Annals. This 2005 paper in the Annals provides some strong properties about empirical Bayes estimators in a problem that's extremely close to the one that I just posed. Actually, the problem I just posed is a subset of the problems they consider. There's a variety of methods to estimate G. I'm not going to go into those methods. I'm only going to talk about it in a very limited parametric way. Let's think about the following exercise. I had the committee meeting at the Fed where all the people came into the room with different priors. I'm going to constrain that committee meeting a little bit. I'm going to insist that everybody uses the same family of priors. That family of priors is going to be finitely parameterized. The parameters of that family of priors are called hyperparameters. Different people come into the room with different hyperparameters for their priors. One of them is going to win. Okay? That's going to be the empirical Bayes estimator of the hyperparameters of the prior. So that's a parametric empirical Bayes. These wonderful theorems are all about non-parametric empirical Bayes, but as we all know, you can get a long ways by doing things parametrically. And actually, you can do worse by doing them non-parametrically in practice. Okay. All right, so some important lessons. One of the big lessons is that these shrinkage and Bayes methods can be very important in this framework. Okay, so that's point one, blessing of dimensionality. Point two, blessing of dimensionality. So instead of curse of dimensionality, blessing of dimensionality. And so now we are going to shift gears and going to talk about dynamic factor models, which might seem totally unrelated, But if you're still here and not catching a plane, towards the end you will see that these are not unrelated. Okay. So I'm going to talk about this in more detail later. So just live with this for the time being, okay? So here's the idea. We have a ton of series, I don't know, 100 or 200, and they are related to something that you can't observe, F. There's only a few F's. Some people say there's 1, some people say there's 9, but there's a few of them. And then there's some other idiosyncratic noise. Sargent had a model like this in his 1989 paper, where he said that you observe some things and there was an underlying state that was evolving, and then there's measurement error because the statistical agencies just added error to data. That was his model. And then this underlying F evolves over time, and I'm going to ignore that for the argument here. This model is a dynamic factor model, and this is what was first proposed by Gaevicke in his thesis. And there were a number of papers that looked at this empirically. So England and Watson figured out a way to estimate this in the time domain using the Kalman filter, and then nobody did anything with it for a while. And then there was a series of papers that used that algorithm in the late 80s and estimated this. And those were all on really small systems. So I guess Mark and I, we had 4 variables. How many did you have with Engel? 5. Okay, and I think Tom Sargent had 6 or something. These are small systems, like 1 factor, and a couple of lags here, and maybe modeling some dynamics here. And so you've got a pretty small number of variables. And this just took a long time to do the MLs. I mean, the MLs were slow back in 1990, and it was tempting to try to increase the number of parameters. I mean, you'd really like to go to a higher system because it would be interesting to see what would happen, but it just wasn't realistic. Okay, it wasn't a realistic exercise. So that looks like a curse of dimensionality. Okay. Well, so in a paper, in a discussion of Quan Sargent, John Gaevicke suggested that actually you could really do a lot better if you had a lot of series. And he didn't really propose any computational methods. It was all just kind of intuition. And his suggestion was that if you had a ton of series, you actually might be able to estimate F well. See, look at this. And so Mark did the Kalman filter, and remember there's the state estimation equation. If this is the state vector F in this setup, so this is the observer equation, and then this is the state, and the state has a dimension of 1 or 2 or something like that, and you only have a few series, you can use the Kalman filter to estimate F, but if you only got a couple of series, you're going to be estimating it with error. So it'd be swell to know F. It'd be really interesting, but you're going to be estimating it with error using the Kalman filter with a small number of series. Gaevicke's intuition was that if you had a ton of series, that you'd actually be able to estimate F arbitrarily well. And I was there at that conference, and I thought he was crazy. I don't know, maybe you thought. We edited the volume. I mean, we left the comment in, but I don't know. Okay, here's an example that shows that what he was saying makes complete sense. And this is following a paper by Forney and Reichland about 10 years ago. So now I'm going to make a really simple assumption. Suppose you have one factor, F. So this is a simple version of that dynamic factor model. And I'm going to say do something totally idiotic. So we're not going to estimate something using the Kalman filter in state space form by maximum likelihood. We're going to compute the average of the x's. Right? So what could be simpler? Well, compute the average of the x's, then it's just the average of this bit here, so just substituting things in. And now this ft doesn't depend on I, so I can pull that out of the summation and then pull the e's out of the summation. And what do I have? Well, I've got a term right here, which is an average of these e's. Well, these e's are idiosyncratic in the sense that they're not really from one series to the next. They're pretty much uncorrelated. You're just going to have a weak law of large numbers telling you that that thing's going to go away. And now if these lambdas, let's say these lambdas are positive on average, that's an identification assumption, so we might want to think about that. But let's just suppose, for the sake of this argument, that these are positive on average. Well, then this thing is just going to converge to some number, and there you have it. Okay? So it turns out that if you have a ton of x's, all you got to do is just average these suckers, ton of x's, one factor loadings being positive on average. Just average these guys, and there you are. You're done. So you don't need the Kalman filter and state space and ML or any of that stuff. You just got it. So this is a blessing of dimensionality. Right? You've got a non-parametric estimator that gives you this really interesting object, which is the factors. Now, this is not the most sophisticated estimator of the factors that you might ever find. It's just averaging these, but this is the intuition for the other estimators that are used. Okay, so that's two interpretations of blessings of dimensionality. Blessing of dimensionality number one being you can not just is the frequentist problem equal to the Bayes problem, but if the number of observations, the number of predictors is large, you're actually going to be able to solve the Bayes problem. That is, we're going to be able to estimate G sub n, and therefore use that estimated value of G sub n to come up with a good forecast. So that's the blessing of dimensionality in the forecasting problem, and here it is in the DFM problem. All right, so now I'm going to talk about DFMs. So now this is probably where you thought I would start. Okay, so here's what Gavricki wrote down in his dissertation. And he said, we're going to write down a little model here. And the model says that I've got a bunch of x's, and they depend on two things. Something that's common, so a common factor, and then something that's not common, and these are idiosyncratic terms. And in the model that he wrote down, he added Gaussian errors and all that stuff, but in the model that he wrote down, he said that these idiosyncratic terms were not correlated from one x to the next x. So between x's, there is no correlation between these. What that means is that the entire co-movements at all leads and lags of the x's arises from this common component, in particular from this f. Now this f, because things evolve over time, it has some time series structure, and so we can just write that down as a VAR. Right? So it's got some time series structure, and it might appear with lags. So, some series might, so in the jargon, load on the f's with a lag. Others might load contemporaneously. Others might load with a distributed lag. Right? So that's the exact dynamic factor model, and that's actually that's what's programmed up in the Kalman filter in those early 1980s papers. So a couple of quick comments. Comment number one is I'll just be clear, we'll come back to this when I talk about SVARs or favars. The factors themselves are only identified up to some rotation. So I could insert a matrix H inverse. In fact, if you wanted, I could even make these a lag polynomials, but I could even make these lag polynomials in this setting. I could insert a matrix H inverse. I could make these lag polynomials if I don't care about one-sidedness, if I wanted to make this two-sided. So I can insert this H inverse in here, and I'm going to get the same product, lambda of L times ft. So there's a lack of identification that's involved in this setup. That actually is not important for any of the applications we're going to be doing. So for the first bit, so if we're talking about forecasting, we don't really care whether we have in some sense f or h times f. We only want the space spanned by f in a regression so we can project it on it. We don't really care. So this is not going to be of any importance at all. It's only going to be important if we start talking about what's a structural shock and what do these f's actually mean. And we'll talk about that at the very end when I talk about Favar and Bovan-Giannoni. Second comment is that there's a spectral factorization. And that spectral factorization is this is the spectral density matrix of the x's at frequency omega. And because the f's and the e's are uncorrelated, that means that all autocovariances between the two and all leads and lags are 0. So that means that the variance, the autocovariance function of the x's is equal to the autocovariance function of this guy plus the autocovariance of this guy. So the Fourier transform of those is equal to the sum of those two Fourier transforms. That is to say, the spectrum is equal to the sum of these two bits. And this is just using the usual spectral algebra. It says here that there's a common component in the spectrum that's going to have reduced rank. So the dimensionality of f, the number of dynamic factors, we're going to call that q. And so the rank of this bit of the spectrum is q, and then this is a diagonal matrix, all right, a diagonal matrix, diagonal spectral density matrix. We're not going to exploit that in anything that we do, but that's just for those of you whose intuition is best guided by relationships in the frequency domain. I think there's one in the audience. Forecasting. So this is pretty interesting, pretty important, and maybe obvious, but it's worth going through these steps. If you wanted to forecast one element of x, given past values of x and f, all right, so this is the magic bit. If you're given past values of x and f, well, given this structure and the fact that it breaks down into this part that depends on the f's and the part that's the idiosyncratic terms, that this forecast is just going to end up being a function of the f's and then your own x. So, I'm sorry, I said that mathematically. This is really the whole, don't look at the math. Look at this equation. Look at this equation. If you want to forecast x, well, you're going to have some serial correlation in the error term, but this error term is unrelated to everything else. So that serial correlation in the error term can be taken care of by throwing x as a regressor, as a lags of x in this equation. And then you've got the f's. So you can forecast x given the f's and given the f's and your past, right, from this equation. And then you could ask the question, would I do better if I had any of the other x's? Like if I have 199 other x's, would it be useful for me to throw them in this regression? And the answer is no. And the reason that the answer is no is that once you've got the f's, so conditional on the f's, all you've got is these e's, and these e's are uncorrelated across all of the leads and lags with all of the other series. So there's no point in throwing on those other x's. All of the information, the dynamic factor model that you need for forecasting is embodied in this f. So if you could get that f, you're in business. Okay. All right. So now that's too strong. That's making assumptions that there's no relationship at all in the idiosyncratic parts. Even if you just take it literally at the measurement error story, you could imagine that there might be some series. There are series that are measured with the same survey, and if the survey is done in a certain way, there's going to be correlation in survey error across the different series. And if the measurement error has more substantive content, then there might be correlation. The approximate dynamic factor model takes that into account. I'm going to give some particular assumptions that are statistical implementations the statistical implementations of the dynamic factor model. But basically, the approximate DFM says that that most of the variation in the matrix of x prime x is coming from the factors, and there's a little bit that might be coming from the idiosyncratic terms, but asymptotically that matrix, the variation in that matrix is dominated by the factors. Another way to say that is that in the x prime x matrix, if there are q factors, it's going to be dominated. There's going to be q really big eigenvalues, and the rest of the eigenvalues are going to be small. Okay, so we're going to translate the static factor model into a dynamic factor model into what's called the static form, which is actually going to be quite convenient for estimation. So to do that, I'm going to take the dynamic factor model and okay, well here, so here's what I'm going to do, which is I'm going to take this. All this f and these lags, and I'm going to assume that lambda vel is finite order, finite degree lag polynomial. So if it's finite degree, say P sub f, then I can write all of these lag polynomials out like this. They're the coefficients of the lag polynomials in the first equation. And then I can take all these f's and I can write them in a vector form like this. And then, of course, that means the first equation is just x1t plus the distributed lag of these f's plus e1t. All right? So I've just written this in first order form, and that's assuming that this has got a finite degree lag polynomial. So under that assumption, this is, here's what I've got, which is I've got xt is this matrix now, which is n by r, and then this vector here, which is the capital F, which is r by 1. Now, the way I've written it out, r is going to be equal to the number of little f's, which is q, times the number of lags, pf. Now, there might be some redundancy, or it might not be that much, but that's the most that it could be. So this is now going to be what we'll refer to as the static form of the dynamic factor model. And it's just written so it looks like it's a regular cross-sectional factor model, but it does have dynamics living inside of it in terms of the lag structure here. In addition, I can take this VAR for the little f's, and then in stacked form, that's just going to imply a VAR for the big f's, and so I've just written that down. And okay, so there's a dimension issue, which is that these f's are r by 1, and these etas are q by 1. So that means I've got to have some matrix, which is going to be r by q, which is going to take this reduced number of etas of the dynamic shocks and turn them dynamic factor innovations, and turn them into innovations for the static factors. All right. So that's the static factor model, and just to make it simple, I'm going to just make this a a VAR1, just so that it's easy to work with. And in most of the rest of the talk, that's just a VAR1, just to make life simple. So there it is. There's the DFM in static form. And this DFM in static form is now just looks like a standard state space common filtering exercise. So that's what it is. You can put the whole thing in state space form if you want to model the dynamics of the idiosyncratic terms, which will be useful. You could imagine that those follow autoregressions, so I can then stack the e's and their lags as much as needed, so that autoregression can be written in first order form, and so that's the first order form of that autoregression. H is now going to be a matrix that takes these n idiosyncratic innovations, zeta, and then transform, and basically has a bunch of zeros in it, so that this is the first order form of the autoregressive representation for the e's. Should emphasize that because the e's are supposed to be uncorrelated across each other in the exact factor model, that this matrix D is diagonal. All right, so these are not. It's not a VAR for the idiosyncratic terms. It's just a whole bunch of ARs. All right, and so then this puts the whole thing, just for completeness, this puts the whole thing into a state equation here, and an observer equation right here, and you're ready to apply the common filter. And so that's how these common filter algorithms were originally done, or versions of this is one way to set it up. Okay. This just is what I said. Okay, so just to step back, let me summarize. We've written down the dynamic factor model. We did just a few things. It's a linear model. Did just a few things to put it in exactly the state space form that you saw for the common filter when Mark presented that a couple of days ago. And since it's now in that form, that means we can run the common filter, and among other things, we can compute the likelihood. If we have the likelihood, we can then maximize it. And so this can all be estimated. These parameters can be estimated by maximum likelihood. And that's what was done. That got sort of frustrating. Qua and Sargent actually were able to estimate a system with 60 variables, but they did it in a very, very special structure that that allowed them to do some tricks that were not readily generalized. So although it looks like it's a big structure computationally, this was, it was certainly non-trivial, but it wasn't really moving all the way towards a full system. Okay, of course, that was a while ago, and computers are better. So I'm going to talk a little bit about MLEs right now. Computers are better. One of the interesting developments, since there was in this intermediate period a fair amount of work on alternative non-parametric estimators of the factors, and those estimators are actually pretty good. What that means is that you can now get, using those preliminary alternative estimates of the factors, you can actually use that to get pretty good starting values. So if you don't know these factors here, but if you could, you had some reasonable estimate of the factors, then you could get a pretty reasonable estimate of phi, and you could get a reasonable estimate of these of maybe of g, and then you could get a reasonable estimate of in your regression. Let me put them in regression form here. You could get a reasonable estimate of the factor loadings by regressing f on lambda, and then you can take the residuals and you can fit an AR2 to those. So all of those parameters can be obtained using very simple OLS type algorithms once you have estimates of these factors. So because we now have procedures that I'll talk about in a minute that give good estimates of the factors, you can get quite good starting values for the. In fact, you can get consistent starting values for the estimate for the common filter. And then I guess a final point is there's some recent work here by Jungbacher and Koopman that provides an additional speed up. It's actually a clever projection device that churned some of the common filter updating equations into just regressions. So there's additional advantages that you can get instead of having to work with the otherwise large matrices that would be involved. There's some theory that's been developed about ML estimation of these systems when you have large of dynamic factor models when you have large numbers of series. And the relevant paper is this one by Does, Giannoni, and Reichlin. And they show that these MLEs are going to be consistent, or I will be more precise than that. What they show is that you will get consistent estimates of the factors by estimating those parameters by MLE, and then by using the common filter to estimate the factors. So I'm going to talk about, there's some empirical evidence, but I'm going to talk about that once we go through some of the other estimation methods. Another comment about the MLE and the state space formulation of this. The state space formulation has a couple of advantages. One of them is, or a couple of nice features, I should say, and one of these is that it's possible to accommodate a large number of data irregularities. So if you have data that occurs, some monthly data and some weekly data, for example, or some daily data, you can actually set up. But then, some days you might observe some macro variables, and those macro variables at those days, this being the observer equation, at those days, the observer equation is going to be related to the factors, but only in a way that links it to the variables that we're actually observing today. So the observer equation is going to have a version of lambda that's going to be varying over time depending upon whether we see it or not. And that allows you to go ahead and compute a likelihood and run the common filter based on the data that you have available today and in the past, even though the dimensionality of that data is going to be changing depending upon the day that you have it. And moreover, you can do things like, say, suppose you have temporally aggregated data, so you want to model consumption as a flow, and what you observe is consumption over the month. You could say, I'm going to average the factors over the last month, and I'm going to observe once every 30 days. I'm going to observe the average of the average of the Fs every 30 days. So you can set up a lot of things like that in the common filter. that's not new. That you can do that is described in Harvey's 1993 book. It's certainly older than that, but Harvey has a ton of papers on this. But it was implemented in this context using a large system by these three authors using irregular mixed daily data. And the nice thing about that is that once you have the parameters of the once you have the parameters of the DFM, every day when new data are released, you just can put those in, and then you run the Kalman filter updated for that one day, and you have new estimates of the state based on that day's information, and those feed into new estimates of your 200 series. So you have in real time updates of everything you'd want to know based not just by some kludgy method like Chow-Lin or something like that, but in a completely internally consistent mechanism that's going to give you an updated piece of information on all of the series that you're interested in. And so Domenico, you were involved with doing this sort of thing at the Fed, isn't that right, with Lucrezia? So I don't know if that still exists. Is that actually running, or was that a hypothetical trial experimental system? Okay. So, once these get running in real time, then they disappear from the literature. But these, this is a sort of thing that can be very valuable because it provides a complete and internally consistent update on a large number of series. Okay. All right. So, if that's estimation MLE, all right. All right. So here's the chronology. Right. The chronology was the original stuff that Gaverke did was spectral, and then Engel and Watson figured out how to do this in the time domain by the Kalman filter. And then everybody gave up on the Kalman filter because it was too hard using the computers that we had. And so then some other procedures were shown to work. And those are principal components families of procedures. But now the computers have gotten fast enough that we're kind of back to doing MLE on these really huge systems. But that's very recent, just the last few years. And I think that this Koopman-Jungbacher thing is going to help a lot in terms of making it implementable. So now I'm going to talk about that intermediate set of procedures, which is principal components related procedures. So here's principal components. So let's, for the time being, think of this as a regression model. Or some model. I don't know. It's some model. I'm going to say we're going to treat f as a... We're going to treat lambda as a parameter and f as a parameter, which sounds idiotic, but let's just do that and see what happens. Okay? So I'm going to say I want to fit this by nonlinear least squares because I can't do OLS. If I knew lambda, I could figure out f. If I knew f, I could figure out lambda. I don't know either of these. But I'm going to do, say, some nonlinear least squares thing to try to figure out lambda and f. It looks like a regression problem, so why don't I minimize the sum of squared residuals? All right, so I'm going to minimize the sum of squared residuals. And lambda and f are parameters, whatever that means. I'm estimating them as parameters, so they're parameters. They're theta. Well, this problem actually has a really nice structure. And I'm going to concentrate out f. So if I knew, let's imagine that I knew lambda, then loosely speaking, assuming that I can do my matrices with the right transposes and all of that in my head, f hat is going to be lambda prime lambda inverse lambda prime x. So the residual from that is going to be x minus lambda prime inverse lambda inverse lambda prime x. So the sum of squared residuals from that is going to be x prime, the projection on the lambda matrix x. Well, I've gotten rid of f which is fine. If I knew lambda, I don't know lambda, but now I can solve this problem. I can say minimize this projection sum of squared residuals over all possible values of lambda. And you look at that and you say, that doesn't look very fun. That would be a big grid search. But if you do a little bit of algebra, it doesn't have to be a big grid search. So minimizing this projection on the orthogonal matrix to lambda is the same as maximizing the explained sum of squares. And now I remember my matrix tricks from graduate school, where I can take the trace and do transposes and pull things to the side, and it's the same answer. And the advantage of that is I got all of these summation things in the middle. And so I want to find the lambda that minimizes this inner product. Well, this lambda prime lambda, the minus 1/2 prime lambda, is normalized so that this thing together is itself prime itself is equal to the identity matrix. So I can replace this, or at least throw away this, and impose that side constraint, and I say I want to maximize lambda prime times sigma xx lambda subject to this restriction. And that's solved just by being the first R eigenvectors of this matrix, and that gives then f hat as lambda hat prime xt is the first principal components, first R principal components. So the reason I did that, principal components is not new, and nonlinear least squares is not new, but in some sense, principal component sounds like this stupid algorithm that you never really wanted to use in SAS, but it actually has a very sensible origination. So the consistency of principal components in the exact static factor model with t fixed and n tending to infinity was shown by Connor and Karachik. And then there's a pretty substantial literature now over the last 10 years that's been looking at results for estimation in the approximate dynamic factor model in static form. Here are some typical conditions. One of them is that you assume the f's are well behaved. Another is that you assume the lambdas are well behaved. So there's obviously some identification conditions lying around in there, but it's basically these are definitions that you have the right number of factors. So if you have R factors, it makes sense that these things would be true. This is the approximate DFM that says that the E's are going to be weakly dependent over time and across series. So there might be some correlation across series, but it's not going to be so much that it's driving the covariance of all of the series. It's just maybe a block of series, like maybe there's some consumption series that are related or something in the same survey that's related. And then the F's and the E's are uncorrelated. And then the asymptotics here are ones that have n and t tending to infinity. And this is going back. This asymptotics works. Remember the Forney-Reichlen take the average of the x's? That worked because n was going to infinity. Okay, this stuff works because n is going to infinity. This is this blessing, if you will, of dimensionality. Okay, so there's some results. So for the DFM, they're consistent. You can use F as a regressor. The original proofs were kludgy and they got fixed up, and that's not fair. The original proofs were good, but it turns out you can get better rates. And so these guys got better rates for using things. And there's also now distribution theory for things like confidence bands for predicted values. Let me make a comment about that. Confidence bands for predicted values are different than confidence than prediction regions. Mark showed you this fan chart. Right? That's not a confidence band for a predicted value. That's the entire range of uncertainty that includes not just your predicted value and its uncertainty, but it includes all of the other bad things that could happen in the future. Right? So confidence bands for predicted value are, of course, of some interest, but in forecasting we want to have the distribution, the conditional distribution of y in the future, which is not just the estimation part of it, but it's the bad things that can happen. Okay? It is possible in principal components to handle data irregularities, and there's some, I believe this has actually been used once or twice. There's some details about how you can do that in an appendix of one of our papers. Although arguably the data irregularities are handled probably more systematically, certainly more elegantly in the Kalman filter setup. And they can be used in the Kalman filter setup in this real-time way. Okay, so that's principal components. Now, principal components, there's some other methods that have been proposed, so let me just go through those other methods that are in this family. These other methods are, so this is easy. This is really easy to understand. So I motivated principal components, not motivated, but derived principal components as the solution to a least squares problem. Okay? Those E's, what if those E's were heteroscedasticity? Then you might not want to do least squares. You might want to do weighted least squares. Or if there's a little bit of correlation in the E's with each other, you might want to do generalized least squares. And so that's what it does. Right? So instead of the identity matrix in there, why don't we put in a different weight matrix? Okay? And so that's just GLS. And it turns out this, you just go through the algebra, this is also an eigenvalue problem. It's an eigenvalue, this is a generalized eigenvalue problem. And the only difference is that now we're looking at the first R eigenvectors, not of the x's, but of this GLS transformation type thing. And so these are the what's called generalized principal components with respect to this weighting matrix. What I just gave you was infeasible because that assumed that you knew this. The tricky part here is thinking about the best way to estimate these. And the reason I say, normally when you say, you go through feasible GLS and you say now you just estimate it and you move on, it's not totally obvious in this circumstance because this is an n by n matrix. This is one big matrix. All right? So an n by n matrix has order n squared elements in it, and if you've got 100 series, you're talking about a serious number of elements in this matrix. So there's a couple of ways that you can kind of get at this, and they're discussed in the literature. Probably one of the simplest ideas is impose the exact DFM structure. So in the exact DFM structure, these E's are uncorrelated with each other. And that says that this is a diagonal matrix, and you've changed it. Since you zeroed out all of those off-diagonal terms, you only have n things to estimate, and so that's easy. And Bovan and Ning suggested doing that. There's some other methods that have been proposed. There's a particular procedure using dynamic principal components that these guys proposed in 2005 to come up with a weighting matrix. The approach we looked at. So if you think about this as a GLS problem, we're only doing there's actually 3 dimensions in which you might want to think about GLS. And so one dimension you might think about it is the heteroscedasticity. Another dimension is the cross-correlation across the E's. But there's actually a third dimension, which is the time series dimension, which is that in the exact DFM, the E's are going to have some dynamic structure. So if you really wanted to be serious about this GLS, you'd somehow be doing heteroscedasticity and a little bit of cross-correlation and serial correlation, and that's a lot. And so we don't do all of that, but we do. This one focuses on the serial correlation aspect. So you can do a Cochran-Orcutt type transformation to the data and then use that as a way to estimate the factors. So there's a variety of things that are floating around out there. So that's the, let's see. This is out of order. I'll come back to this. Let me go through the slides in the right order, in the order that the slides are written, and then I'm going to come back to this. So, a logical question is I've presented a whole bunch of different things. I presented MLE and principal components and generalized principal components, and there's at least 3 flavors of generalized principal components. And what is a poor practitioner to do? And that slide should be next, but it's actually in about 7 slides. So just deal with it. Okay. All right. So let me, once you've got these factors, what can you do with them? And going back to the original motivation, is that in some sense these factors are sufficient statistics for all of the other x's in the exact dynamic factor model. So if you're trying to make a forecast, if you're trying to run a VAR with 200 series, but somebody said that you actually have some of those of these factors, you say, this is great, I can throw away all but the factors. And maybe you'd want to use your own lags, but you don't need any of the other series. So you can just put them in as regressors. One of the theoretical results I mentioned, both in the Stock-Watson 2002 paper and the Binding 2006 paper, provides certain conditions under which these factors are useful as predictors. One thing that I guess I didn't emphasize, but I would like to emphasize, is that you really have to. This is really hard. You really have to. This is so different than almost all of other econometrics, in the sense that the ends that we're talking about here are really big. Okay, there's a large number of series, and the asymptotics and the econometric theory reflects that. Remember when we were talking about many weak instruments, right? So, or if you're talking about optimal GMM estimation through sequences of things. So think about all of those econometric seminars that you left in the middle of. Right? The moment you left was when they wrote up these technical conditions, where we're going to look at spline estimators, where there's k splines, and we're going to assume that k tends to infinity, but it doesn't tend to infinity any faster than the cube root of n. Okay? Or you were at a spectral density estimation thing where they had the bandwidth tending to infinity, but the bandwidth divided by the sample size, what is it supposed to be? Cubed again? Cubed. Tends to 0. Or it's, some kernel estimation seminar where the bandwidth of the kernel, well, this is going to be a little bit different, but it's the bandwidth of the kernel has to tend to 0, but it has to, this is in the reverse, be n cubed or something like that tends to infinity. I probably got that one backwards. Okay, so no, I get that. I will. The bandwidth one is too hard. That's upside down. Okay, so but it's the same idea. Or the optimal instruments. We're getting back to GMM. The optimal instruments. They say we're going to come up with something that's equivalent to GMM, and we're going to do it by approximating the score using some sequence of instruments that's going to give us projections, and this is so cool. And the sequence is going to have the number of instruments tending to infinity, but the number of instruments over the sample size cubed tending to 0. And in many weak instruments, the many weak instruments thing, remember how I did the sequential asymptotics where you had, I took t to infinity and I got my weak instrument lambda plus z v prime zu over lambda plus z v prime lambda plus z v. And then I went down here to go to infinity, taking k to infinity, and I let k tend to infinity, but for that to be justified, I had to have k over t to the 4th go to 0. Okay, so all of these things are fake infinities, okay? So you're supposed to have, it's like what Mark was saying this morning, you're supposed to have bandwidths that have sort of infinite lags, but they have to be infinitely small by a big ways to be able to estimate them precisely. These are all fake infinities. This couldn't be more different. The results for by Ning are n squared over t tends to infinity. N squared over t tends to infinity. Have I got this right? Let me get the result. Let me get the rate properly, okay? Okay, now n squared over t tends to infinity, okay? So that's a by Ning rate. Think about that. It's just an enormous number of n. So, if you have 100 observations, you should be looking at a lot of n's. Now, this is just how the asymptotic works, and it doesn't really tell you what the scale is supposed to be. So the only way to really figure that out is to do Monte Carlo simulations. And when you do Monte Carlo simulations on spectral densities, and you look at sizes, when you use optimal Andrews things, you get rejection rates of 40%. Wasn't that what we had this morning? But when you do Monte Carlos here about whether or not it really works to estimate the factors and whether it really works to run regressions with factors as predictors, and you have a couple hundred observations and 400, or you have 50 observations and 100 series, it works great. It works great. And that's just a statement about Monte Carlos. It's not a statement about empirical reality. So it's a completely different world. Okay. Now, where are we? That was a digression. Oh, yeah, multiple horizon forecasts. This gets to this really interesting topic of direct versus iterated forecasts. I could tell. I was sitting in the back, and I could tell that everybody really perked up during that part of the conversation. When Massimiliano approached us with this project, we just thought this was so stupid. It was such a boring project. But it turned out to be pretty interesting, I have to say. There's two ways to do this. So there's two ways to do your direct versus iterated forecasts. And actually, I don't think that we have a good sense, we meaning the people who are involved with this empirically, in the context of DFMs as to which of these actually works better. And one way is you could take your factors that you've estimated, say by principal components or dynamic principal components or maximum likelihood, by maximum likelihood or generalized principal components or principal components, and you could use them as regressors in an h-step ahead regression. Nothing stops you from doing that. You can include lags of your own variable. This is what most of the literature does. Another thing you could do is you could just do one step ahead and then you could iterate. And this kind of has a VAR-type flavor. It seems to be restricted because there's no feedback from the X's to the F's. There's not supposed to be, by the way, right? Because if you know the F's only, you don't need the rest of the X. That's the point, right? So you don't need all those X's in there. But you could iterate this. And I don't think we have good empirical evidence one way or the other as to whether one or the other of these is better. This is the vast majority of the empirical work. If you're doing this thing in the context of I'll tell you one disadvantage of the direct forecast that I don't think Mark mentioned is that every horizon is a different forecasting regression, and that means you have this. It's not completely internally consistent. It's not all generated from the same model. There's all these different models, and one nice thing about this is that it's all from one model. And if you're doing this in the Kalman filter, it all just naturally is going to come right out. So I think that's something that somebody who wants to write a really fascinating paper can investigate whether the direct or iterated forecasts are actually working better empirically. Okay. And you can evaluate these using the data sample methods. All right, let me talk briefly about something called dynamic principal components. So one of the things that was developed, so remember the chronology. Gaverke, in his thesis, did this all by spectral methods. Sargent and Sims did it by spectral methods. Problem with the spectral methods is you could do things like try to figure out the number of factors but you couldn't actually estimate the factors. You couldn't use them for forecasting. All you could say is at the bottom, at the end of the paper, you say, so the rank of the spectral density matrix is 2, which is not, it's not the most interesting thing to say. It's all right, but there's more you'd want to say. So then you go to the time domain things and the MLEs. The MLEs kind of hit a wall computationally, and then people are thinking about other stuff. Some of them were principal components, but one of the other things that was thought of by the for this Forney, Holland, Lippy, Reichlen group, the Euro collaborators, was using a device that was developed back in the 60s by David Brillinger, and that's called dynamic principal components. Dynamic principal components is actually principal components analysis done in the frequency domain. And so you estimate the spectral density matrix now as a function of omega of the entire x's, and then you do principal components frequency by frequency, because at each frequency we saw that there's this spectral decomposition that says there's all the cross things have this reduced rank matrix plus then this diagonal piece. And so that's the structure of principal components in the time domain in the classic psychometric setup. And so instead you just flip it around, you do it in the time domain, in the frequency domain, and that's going to give you these so-called dynamic principal components. And then you can do some inversion and actually get back stuff in the time in the time domain by doing since you've essentially. So one way to think about that is that this is not the way it's actually done, but this is a way to think about it. Mark showed you that you can take those matrices that he called H, and you can factorize the entire covariance matrix of the data. So and those H matrices were the discrete Fourier transforms, so you go to the frequency domain. So you could go H inverse and going from the frequency domain to the time domain. So once you've parameterized the entire autocovariance function in this reduced rank way in the frequency domain, you can H inverse everything. You have the time domain full covariance matrix of the entire data, and if you then make assumptions of normality, once you've got all of the data and the full covariance matrix, you can come up with any conditional expectation that you want, and you can think about expectations of the factors. Now, that's not actually how it's done. That's just how I think about it, but that's not how it's done in practice. The problem with this method, and I think the reason that the method isn't used much anymore, is that it produced two-sided estimates of the f. So if you want to think about any application where you'd want to have a one-sided series, like forecasting or any application like that, you're not going to actually get this one-sided. You're not going to get the dating right. It's going to include future information, and that's problematic for most applications. It is the case that this factorization can then be used to provide potentially improved generalized principal components estimates, and that really, whether that helps or not, is essentially a Monte Carlo and empirical question, which we'll look at. Okay, in fact, now here's the slide that I was looking for, which is what should you use? So what's the poor practitioner to do? We've got a whole ton of things. We've got MLEs, principal components, generalized principal components, of which I've listed 3 flavors, and there's actually more flavors than that. And so what's the poor practitioner to do? And that's a good question. There's a little bit of theory. Okay, so here's piece of theory number 1. Piece of theory number 1 is hypothetically, let's just suppose that you knew the parameters of the dynamic factor model. Okay, just suppose you did. Then the optimal thing to do is actually quite straightforward. At least in the exact dynamic factor model, you should estimate the minimum mean squared estimate of the factors, and that's obtained by running the Kalman filter. Right, so it's clear that the Kalman filtering approach is the best way to estimate the factors in the exact dynamic factor model. That's assuming that you know the parameters. There isn't any theorem that I'm aware of that says that the best estimates of the f's are obtained by applying the Kalman filter using the MLEs. It sure stands to reason that that's a sensible thing to do, but there's no theorem that says that. The only piece of evidence that we have at a theoretical level is a comparison by Choi, where he compares the asymptotic variance of principal components to the asymptotic variances of generalized principal components under the exact dynamic factor model structure. So you assume exact dynamic factor model, and then on the one hand you do principal components, and on the other hand you use generalized principal components. And he does it for the infeasible principal components, and he finds that you get a smaller covariance matrix. I don't think that you get more precise estimates using the generalized principal components. I don't think that that's a very surprising result, because if you knew, remember the generalized principal components uses the covariance matrix of the errors inverse. If you knew that, then sort of it seems kind of obvious that that's what you'd want to do to estimate the parameters, and so it's not a big surprising result that you would get those improvements. I think it's much less obvious, because that's such a huge matrix, it's less obvious that if you estimated it, you would necessarily get those improvements. I think I suspect that this is not impossible. I suspect somebody could do this. I suspect somebody could work out the algebra. And I think that would be a great project for a diligent graduate student. Okay. It's a good question. There is some simulation evidence. A lot easier than the algebra is the simulations. And Choi produces some. And although his theory only does for infeasible GLS, he actually produces some results for feasible GLS also. And what he finds is that for feasible GLS, it's one of these things on the one hand and on the other hand. And depending upon the design, and depending how big n is, sometimes it's better to do principal components, and sometimes it's better to use feasible GLS. And there's really no clear bottom line from those simulations. There's a nice simulation study in this Does, Giannoni, and Reichland paper, and they look at principal components and principal components. I didn't say this. This is a really cool idea that makes just so much sense that's developed in one of the Euro people's. I have a reference in the slides. One of the Euro group's papers, which is just doing what they call a two-step. All right, the two-step is you estimate the factors by principal components. You then regress the x's on the factors to get the lambdas. You take the residuals, you get the e's. With the e's, by OLS, you can estimate the autoregressive coefficients. In the F, if you've got the F's, you can regress the F's on the past, and you can get the factor state dynamics. You take all those equations, you plug them in, those coefficients, you plug them in, and now do a single pass of the Kalman filter. Don't do any parameter estimation, but just do a single pass of the Kalman filter to get an updated estimate of the F's. All right, so that's really easy, because you're not doing any nonlinear optimization for the parameters, and the one pass of the Kalman filter is no big deal. And so that's something they look at also. And then they look at the full ML of everything using an EM algorithm. And what they look at as this measure is a measure that we looked at before in some of our earlier work, and a lot of folks have looked at, which is basically if you have a bunch of F's, what you'd like to do is you'd like to have the estimated F's equal the true F's, and you can think about projecting the true F's on the estimated F's, and then this is sort of like a trace R squared for a regression of the true F's on the estimated F's, and you'd like this R squared to be 1. And okay, so what do we have here? And now we're looking at ratios of trace R squareds. So this is a table from these guys, Doge, Giannoni, and Reichland. And so this is the ratio of the trace R squared for maximum likelihood to the trace R squared for principal components for one of the models that they're looking at. And the really interesting result for this model is that the principal components and maximum likelihood are giving just about the same trace R squared. Okay. This is the ratio of maximum likelihood to two-step. You see, so for n equals 10, so this makes so much sense. Look at t equals 100 and n equals 10. All right, so t equals 100 and n equals 10 is kind of not quite, for the old literature it was like n equals 5, but this is kind of in the flavor of the old literature. And maximum likelihood is doing better than principal components. And in fact, maximum likelihood is doing better than two-step. But as you start going to infinity, or getting bigger, principal components is doing just fine. And they have other simulation results, and they have sort of the same flavor in their other simulation results. So I take that as evidence that, the ML is clearly giving some improvements. There's no question about that for the small ones. It certainly is never hurting anywhere. On the other hand, the actual gains when you have a large number of series seem to be modest in these simulations. And that, this is just a simulation, so it could be more substantial in other simulations. Okay, so Bovan and Ning have also some simulation evidence comparing principal components to generalized principal components. And so I have a table of results. And so the columns to compare is this. I don't know what this column here. So I looked in their paper, and this is the column for principal components with an unrestricted regression divided by an autoregression as a benchmark, and this is generalized principal components. This is the particular covariance matrix scheme they're using is just the weighted least squares version, the heteroscedasticity version. And if you compare these columns, so at one step, let's look at 4 steps ahead. In this simulation, that's a calibrated one off of real data, 0.64 means that you're doing much better relative to an autoregression by using this particular procedure. You're getting improvements of about 40%, 35%. And if you use generalized principal components, it's 0.67. If you use regular principal components, it's 0.64 for personal income. It's 0.69 versus 0.69 for MSMTQ, which must mean something. It's 0.69 to 0.7. I should know what that is. Manufacturing and trade sales. LP-NAG is non-agricultural employment, and you get just a tiny improvement by using principal components. If you look at this, here's a case where using regular principal components at the 6-month horizon for personal income isn't as good as using the generalized principal components. Basically, there's no difference. Okay, so in their simulation, you can split hairs and maybe look at second decimals or third decimals, but basically there's no difference. Okay. So that suggests that principal components and generalized principal components make really pretty modest difference. I'd say that in our work we would basically agree with that. There's some empirical evidence. The broad summary of the empirical evidence is that these things really have fairly similar performance, the different flavors of principal components. I guess so this is more an impression on my part rather than, this is impressionistic, which is, it seems as though in the versions that are estimating a ton of parameters for the feasible GLS, that those can be prone to outliers in both directions. Sometimes particularly good, but sometimes particularly bad. Now, when I say particularly, it's not. We're not talking about huge outliers. We're talking about 2 standard deviation blips in 0.89 compared to a 0.94 or something like that. But there seems to be more variability in the generalized principal components approach. Here's one nice picture. And so this one now is comparing principal components versus the filter. This is one realization from a paper by Rees and Watson, which is comparing one realization of a filtered ML estimate of in a single dynamic factor model with a bunch of price series to principal components. And one reason this is kind of interesting methodologically is that these, as you know, price series are incredibly noisy. So the R squared, the fraction of the variance that's explained by the principal components in any one of these regressions is reasonably small. So you can think about this as not being a particularly dominant factor. And so what you see here is supposed to be in color. Does that appear in color? But not really. Well, there's a smooth line and there's a bumpy line. Okay, so if you're still awake, do you think the smooth line is from the Kalman filter, or there's a bumpy line from the Kalman filter? The smooth line is from the Kalman filter. All right? The thing that the Kalman filter does is it does the cross-sectional averaging, but it actually does a little bit of temporal averaging as well, and that's going to give a smoother estimate of the common factor. And just sort of looking at this, a common factor that has that smoother estimate kind of is sensible. Whether that translates into forecasting improvements, I think, is a question that we'll just need. We broadly defined need a little bit more experience on, but it certainly, in this example, it looks quite promising to be giving improvements. Okay, so this is a good place to break. So we'll come back and talk about selecting the number of factors or estimating the number of factors. The smallest, and they look like this, and then you figure out what's big and what's little, and just by looking at it, and then you decide that there's 7 big factors. Okay, so that's one way to do it, and it's not useless. It has until very recently had no distribution theory associated with it. So I'm not going to go into any of that. Let me talk a little bit about some methods for estimating factors. So there's the main procedure that's used right now is something called the binding information criterion. And looking around this room, I think for the benefit of being expeditious, since I'm left with mainly the hardcore econometricians, I'm going to the next. Oh, wait, one or two. Well, I have a long series of slides that's for general purpose edification, which is what's an information criterion, and I was going to relate that to Bayes and Akiyuki information criteria in terms of estimating the lag length in an ARP, and so I will give you the very brief version of that. An information criterion. So suppose you don't know P. You want to run an autoregression, and so here's the game we're playing. So the game we're playing is that it's an autoregression. You know it has finite order. The order is no more than a certain number, 7, and you just don't know what it is. It's less than, maybe it's 7, maybe it's 6, and you want to figure that out. And if you do sequential testing, like if you do 5% significance testing, if you go from the beginning to the end, that's a bad idea because you could have an autoregression where the first coefficient is 0, and you never get beyond that. And you could you go from the other direction. If you're just doing hypothesis testing, you've got a type 1 and type 2 error that's going to end up not going away. So information criteria get around that and provide a way to provide a consistent estimator of P. And the way it does it is it says, I'm going to ask you to trade off. If I look at the lag length P, I'm going to provide you with an objective function. And the objective function is going to do 2 things. I'm going to say that as you increase P, you're necessarily going to improve the fit. The R squared has to go up. The sum of squared residuals has to go down. So you're necessarily going to be improving the fit, but I'm going to penalize you. And the way I'm going to penalize you is add in a penalty factor that is increasing. Actually, I drew it as a curve, but it increases linearly in these as you add P. As you add more lags. And if you then add these 2 together, there'll be a minimum, and that minimum is going to be your estimate of the lag length. And so the whole trick is figuring out what the slope of this penalty factor should be. And the theory of the theory basically says that if this penalty factor goes to 0, but it goes to 0 slowly, then you're going to get a consistent estimator. And so the way that the proof works is that you look at 2 cases, the case that you underpredict, and you show that that can't happen. Well, why couldn't you underpredict? Well, okay, to underpredict, what you'd have to be doing is giving yourself a really big penalty, because by underpredicting, you're necessarily losing some gain from the sum of squared residuals. being decreased. So you've got to be using a really big penalty factor to underpredict. So if your penalty factor goes to 0, you're not going to underpredict. To overpredict is kind of more subtle because you'd love to overpredict just by maximizing the R squared and minimizing the sum of squared residuals. To overpredict, for that not to happen, well, you have to be using a penalty factor. It can't be too small. So the penalty factor has to be, well, it can't be too small. And if you choose it just right, then you're not going to overpredict. And so there's a proof in an introductory econometrics textbook for undergraduates that does that. Okay, so the Bi-Ning criterion is exactly the same thing, which is it says I'm going to look at the log of the sum of squared residuals divided by the sample size with a penalty factor. Log of sum of squared residuals is a little more complicated because it's not just a regression. We've got this big matrix X, and we're fitting everything to the matrix. So the log sum of squared residuals is going to be, well, you could do it as a trace way, or you could do it as a sum over T and a sum over I of fitted values of given residuals. And so, but that's basically the sum of squared residuals from doing this fit. So it's not, by the way, the generalized least squares sum of squared residuals. It's the regular OLS sum of squared residuals. And now you got to add a penalty factor. Well, this is a bizarre penalty factor. The BIC penalty factor was log T over T, which goes to 0, but it doesn't go to 0 too quickly. This is very strange. This is n plus T divided by n times T times the minimum of n and T. And you say, well, where does that come from? And it actually turns out to be quite clever. And what it's supposed to do is it handles n and T getting big at lots of different rates. But n and T both have to get big for this thing to work. Suppose that n is fixed, then this is going to cancel, and this is going to get big at rate T, and it's not going to have a penalty factor that goes to 0. If you want to plug in a case where n equals T, then you work it out. I'm sorry. Oh, wow, I have an important typo right here. This is an important typo. Ready? The whole purpose of this was to give you the formula for what seems to be in practice of the various information criteria that have been produced, the one that seems to work the best in Monte Carlo simulations. And that's Bai and Ning's ICP2. And I typed it wrong. That's bad, okay? It's got a log in there. This is it, okay? It's right on the next page. Here's the intuition for why this actually is pretty sensible. BIC works pretty well. I mean, that's the recommended procedure for an autoregression if you don't want to overestimate. AIC will give you some overestimation. AIC overestimates with finite probability asymptotically. Suppose that n equals t. Then we have 2t here, and we have t squared down here. So that's going to be 2 times t over t squared, which is 2 over t. N equals t, then the minimum of n and t is t, so it's going to be 2 log t over t. 2 log t over t. That's BIC. That's the BIC criterion. Okay, so this actually is pretty sensible. It's very much like BIC. BIC works well, and this seems to be the one that works the best in practice. Now, that said, in practice, different information criteria can yield really quite different answers. So, and there's some delicacy, and you have to use judgment. So, like any empirical work, you have to think about what you're doing, not just mindlessly apply a procedure, and then when it says that there's 29 factors, you just sort of say okay and estimate 29 factors. I have never seen it say 29 factors, actually. I haven't seen it say 9. Okay, which might be sensible or not. Okay, and let me make a brief aside about estimating the number of dynamic factors. That was estimating the number of so-called static factors, which is the number, because this is this principal component's objective function. The number of static factors is not equal to the number of dynamic factors. In fact, if you remember, the number of the way we derived the static factor form was by stacking the dynamic factors. So in principle, there's potentially quite a few fewer dynamic factors than static factors. Maybe, maybe not, but it depends on the dynamics. So for some purposes, you might want to estimate the number of dynamic factors. Basically, so here's the basic idea of how you can go about doing this. This is the static factors. Suppose that you actually knew the static factors, the F's. If you ran a regression of the F's on their lags, you're going to get some residuals from that VAR. That VAR of F's on its lags is going to have some residuals. The rank of those residuals is actually going to be the rank of the number of shocks of the dynamic factors. So the intuition here is take the principal components, run a regression on their lags, and then look at the rank of the residual matrix. There's a number of different ways that can be implemented. Amundsen, Watson have one approach to doing it. Bai and Ning have another approach to doing it. There's a paper that came out in JASA that has a completely different, it's the same fundamental idea, which is a rank efficiency idea, but it's implemented in the frequency domain. I'm just going to refer you to those. We did, in some work that we've done a bunch of Monte Carlo simulations on these, and we didn't think that any of these methods particularly worked very well, but I don't know, Mark liked Amundsen Watson. All right, so, all right. Testing. Let me say just a couple of words about testing. This is an interesting digression, interesting to some econometric theorists. This is actually an ancient and a very difficult problem. So one question that you might ask, I just gave an information criterion approach. A different approach, go back to the autoregression problem. One approach is estimate the lag order. Another approach is simply, can you test the hypothesis of 3 lags against the alternative of 4 lags, or 0 lags against the alternative of 1 lag? That's a well-defined problem. We know how to do that using t-statistics and f-statistics and all that. Here you can ask can we test the null hypothesis of no factors against the alternative of 1, or can we test the null hypothesis of 1 factor against the alternative of 2? And it turns out that's actually a really difficult problem. If the data are exactly normally, if the data are IID normal, so if the x's are IID normal, then the x prime x matrix is going to be a Wishart of degrees of freedom, a Wishart that has the dimensionality of the number of series, n by n, and of degrees of freedom that's t. So that's going to be a Wishart. If the x's are IID standard normal, then that will be a Wishart matrix. There's well-developed theory in Anderson, 1984, summarizes all of that, multivariate analysis on the distribution of eigenvalues of Wishart matrices, and so that's well understood. The trouble with that is that the assumptions that I just made, IID standard normal, is not at all of interest in the practical applications that we're looking at, and those distributions that exist are actually very delicate to that normality assumption. There's no asymptotics until very recently, and recently it turns out that something that these theoretical physicists, some theoretical thermodynamics did in 1994, Tracy and Whittam, applies. And so some guys at Stanford, Johnston, and then a student, El Karoui, were able to generalize the Tracy-Whittam distribution. What's the Tracy-Whittam distribution? The Tracy-Whittam distribution is an asymptotic distribution for the maximum eigenvalue of that Wishart. And it turns out it goes to some really bizarre limiting law called the Tracy-Whittam law. And they were able to generalize that. Recently, Onatsky has tried to apply these to the problems, Alexei Onatsky at Columbia has tried to apply these to problems of dynamic factor modeling, where we now have a much more complicated setup than just this IID Gaussian thing, where there's going to be a variety of potential correlations and so forth. And he's made a couple of important steps. And one of the steps in a paper in 2007, which is very cool, which he solved a classic problem, which is in the cross-sectional factor model. what's the distribution of the scree plot, right? And so he solved that. What's the distribution of a group of k largest eigenvalues in the classic static factor model? That still isn't quite good enough for the dynamic factor model applications. There's a paper of his that has a test. I think this test is not ready for prime time, but it's an interesting line of research, and I think it's promising. And we'll just have to see how this plays out. But it's a potential additional tool, not really ready for practitioners at this point, but it could prove to be a useful tool in addition to these information criteria of Bai and Ning.